Software is all around us. We use it for entertainment, we use it to monitor our health, we use it for business, we use it to keep us safe. But unfortunately, software failures happen in practice. And they happen because software is a human-made product that's incredibly complicated. Now, you've talked about testing in prior courses before, but what we're going to do here is we're going to look more deeply at automated systematic testing, the kinds of testing that are used in large modern software systems in practice. We use software every day to enhance our lives. And unfortunately, the software we use sometimes has small bugs that kind of annoy us. But other times, these bugs can be extremely large and even dangerous. Now, automated software testing approaches are all about finding bugs at development time in a reliable and repeatable way. Even though we have systematic testing approaches, developers still see defects escape into production. So how does this happen? Developers are smart people and they know how to test their code. So why do we still see these bugs in practice? Defects arise for a diverse set of reasons. These vary by product, by team, by process, or by domain. So how do these defects actually manage to sneak into our system? The largest category of defects actually arise from faulty requirements. So one easy way to think about this is garbage in, garbage out. If we specify the software incorrectly in the first place, we're going to build the wrong software in the end. So we need to think really hard about those specifications. So if we specify our software incorrectly, we're going to build the wrong software. If we specify our software incompletely, where we haven't thought about all of the edge cases that are sure to happen at runtime, we're also not going to build the right software. The next category of defects come from ignored or modified requirements. And this is where we've gone and made decisions at development time to help satisfy the development team, usually to deal with time pressure, but might not be the right thing from the customer's perspective. So while changing a requirement can be good for us as developers, from the customer's point of view, the software now doesn't behave the way that they actually expect. So ignoring the requirements can be good for the development team, but are often problematic for the users of software systems. Next, we have design errors. And design errors occur when we take our high-level specification and we translate it down into a low-level design. After that, we have implementation errors. And as developers, we might think of implementation errors as the most common form of fault. And this is where we translate our low-level design into actual source code. Right? So if we miss a guard or make a small mistake in the code, an implementation error will have happened. After that, we have untested implementations. So if we're really in a hurry, we might decide, we're not going to test that code. We can't possibly have made a mistake. But at the same time, we won't know that it's actually working. And finally, we have procedural errors. And these happen when the user doesn't follow the specifications. So procedural errors are also known as user error. And while software systems should guard against this to some degree, we can't always anticipate all of the strange and crazy things that users will do with our software systems. So how can automated testing approaches help decrease these kinds and these classifications of errors from making it into our systems? Automated testing is all about executing our system with a variety of different inputs and outputs and validating that the behaviors of the system are actually correct. Now, this is great, a fantastic way for testing that the design of our system is right and that the implementation of the system is also correct within the bounds of the specification. But one underappreciated aspect of automated testing is the effect that it actually has on the specification itself. Because creating automated test cases require us to go back to the spec and look at it very closely to really capture what the expected and unexpected behaviors are. So here we go. All we need to do is write a whole bunch of automated tests and our system's going to be perfect. It sounds really easy, right? So why do we end up having problems with this in practice? Automated testing approaches have one huge shortcoming in practice, and that's that they can only show the presence, not the absence of defects. And this is because the users of our systems have different data than we do, they have different environmental constraints, they have different expectations, they have different underlying environments than we will have access to when we're developing the software. And we can't possibly account for all of those up front, but we might want to. It's easy to think that all we need to do is to invest more and more time in testing, and eventually we can make our software perfect. But in the real world, we ultimately need to ship. Right? If we don't ship our software, we won't be able to make any money. If we can't make any money, we can't pay the development team, and that's what we all want. So we need to make sure that this actually happens in practice. So given that constraint, given this ultimate temporal constraint, how can we make sure that our systems actually get built the way that we want to? We want to find the defects in our system, but we just don't have time to find all of them. So how can we change our mindset to make this work a little bit better? One way is to think about testing as more of an actuarial process. And when we're thinking about testing from this point of view, what we're trying to do is we're trying to balance the risk of a defect against the costs associated with finding that defect. So instead of saying we want to find all the bugs, instead we're trying to say we want to find the most impactful bugs in the time available to us. So this is a kind of a hard process when you think about it, because I just said a second ago that we don't know what all the bugs are. So prioritizing the bugs to say these are the most impactful ones is not really possible. So how can we go about building an understanding of how we should approach this testing process, this testing problem, given the fact that we don't know what all the bugs are in advance? Effective automated testing really requires having a clear, high-level testing process. And this process is going to vary from product to product and team to team based on the requirements of the system that's being built. So when we're coming up with this product process, the first thing we need to do is to choose what we're actually going to test. Because software systems are extremely large, and testing the whole thing can be really expensive and problematic in practice. So really reasoning about the parts of the system that are most important to test is an important step. Next, we need to actually create the test cases. And when we think about testing, this is the step that we're most often thinking about, right? So what tests need to be created? What do these individual test cases and assertions need to look like? After we've created tests, we need to execute them. So when we're executing the test cases, it might sound like a straightforward thing. Yeah, you just run the tests. But in practice, you need to decide how they're going to be run. Should they be run by the developer before they commit the code? Will they be run on a continuous integration server? Will we run all of the tests on each change individually? These are the kinds of high-level decisions you really need to make on a team-by-team basis. Next, we need to examine the results. Because if you're running the test cases on some continuous integration server that's running in the cloud somewhere, but you never log in to see what happens, they're not going to give you any value to your team. So how do you actually think about examining these actual results, right? For another example would be in terms of the developer. If they're running them locally, the tests locally on their machine, are they allowed to commit code that fails tests? And this is what happens when we're thinking about this kind of step. And finally, what we need to do is evaluate our actual testing process. And this is when we're being introspective about the kinds of steps we've gone through while we're testing the system itself. Because it's natural to have taken shortcuts at some point or other. But we need to think about, have we gone through and tested our system well enough to give us the confidence that we need to actually ship our product? And this is what every team should really do, should spend a little bit of time being introspective, thinking about their overall testing process to make sure it matches the needs of the system that they're building in practice. So in the rest of this module, we're going to examine the testing process in depth. Now let's think about this in terms of an analogy. If you have a car and you want to evaluate how it works, or if it's working correctly, what are you going to do? Well, the first thing you might do is open the hood. Crack open the hood and take a look. Check the oil, check the spark plugs, make sure that all the belts are tight and everything. And that's one great way to test a system. And this is actually known as white box testing. Right? This is where we open the hood and we've looked inside. We can actually see the internals. Another way to test and make sure your car is actually working correctly is to get in, turn it on, make sure it sounds right, drive around the parking lot, take it out onto the freeway, right? But this is testing the car without actually looking at its internals. And this is known as black box testing. Next, what you might want to do is open up the manual for the car and read what the specification is. How fast can we expect it to accelerate? What's it supposed to do when the oil runs low? Right, so what are the rules? What is the specification for this car? And this is how we really build up an understanding what assertions we can ask about the car when we're going through white box and black box testing. And finally, you might come at testing from more of a manufacturer's point of view. So if you're a manufacturer, a car maker, how can you enhance the testability of your car? Because cars are long-lived products. We want to make sure that they're working over time. And when they go in for service, we want to help the service technicians fix the car as effectively as possible. And one way the car industry has dealt with this is through the OBD port. This is the onboard diagnostic port, where when you go into the shop, a mechanic can just plug a little cable in under your dash and download all kinds of really interesting information from your car's computer. Right, so this is one way that the testability of the car has been enhanced by the auto manufacturers to make white box and black box testing easier. So in the rest of this module, we're really going to step through these 4 aspects of testing and see how they apply to modern software systems.